You feel time passing right now. That feeling is real. The passing isn't. Physics has known this for over a century. The equations of physics, every equation I've worked with, every equation that successfully describes how the universe behaves, do not contain anything that corresponds to the flow of time. They contain time as a coordinate. Coordinates don't flow, they just sit there, labeling positions in a four-dimensional structure. The sensation of time moving, of being carried forward from past to future, of now being different from a moment ago, is produced by something, but that something is not a fundamental feature of the laws of physics. It's something we need to explain. And explaining it leads to one of the deepest questions in physics. Let me show you how deep. Newton thought time was absolute, universal, a single clock ticking in the background of all events, the same everywhere for everyone. Events have definite times. Simultaneity is a fact. Two events either happen at the same time or they don't, and all observers agree. Einstein destroyed every part of this. Time is not absolute. It is observer-dependent. Two observers moving relative to each other measure different time intervals between the same pair of events. Not because their instruments are imprecise, because the time intervals actually are different. Time itself runs at different rates for different observers. The twin paradox makes this concrete. One twin stays on Earth, the other travels at near the speed of light to a distant star and returns. When they reunite, the traveling twin is younger, biologically younger, having experienced less time. This is not a thought experiment. It has been confirmed experimentally with atomic clocks on aircraft. Clocks flown around the world come back having ticked fewer times than identical clocks that stayed on the ground. The difference is small but measurable, and exactly as relativity predicts. GPS satellites move fast relative to the Earth's surface and sit higher in a weaker gravitational field. Both effects, special relativistic time dilation from velocity and general relativistic time dilation from gravity, change the rate at which time passes on the satellite relative to the surface. If these effects weren't corrected for, GPS positioning would accumulate errors of several kilometers per day. The corrections are not small adjustments to a Newtonian system. They are essential. The system works because relativity is right. What this means for now, if two observers in relative motion disagree about which events are simultaneous, which events happen at the same time, then there is no universal present. The present is frame-dependent. What is now for one observer is not now for another, moving differently. The feeling of a single universal now that we all share is incompatible with the physics. The most natural interpretation of relativity is what's called the block universe. Space-time is a four-dimensional structure. Past, present, and future exist equally. The past as real as the present, the future as real as the past. The word now picks out a location in this structure, the way here picks out a location in space. Here doesn't move. Now doesn't move either. What moves is our experience of it, and that movement is something we need to explain separately. If time doesn't flow in the physics, why does it feel like it does? Why is there a difference between past and future at all? Here's the most striking fact I can give you. Almost every fundamental physical law is time-symmetric. Write down the equations of classical mechanics. Run them forward. Particles move, collide, interact. Now reverse all the velocities of all the particles. The equations still work. The reversed motion is a valid solution. The laws don't prefer either direction. The same is true of quantum mechanics, the same is true of electromagnetism, the same is true of the strong and weak nuclear forces, with one very small exception that I'll note but not focus on. For almost all of physics, the laws treat time the same in both directions. And yet, you know that a glass that shatters on the floor doesn't unshatter it. A drop of ink dispersed in water doesn't reconcentrate. Heat flows from hot objects to cold objects, not the other way. You know that causes precede effects, not the reverse. You experience time as having a direction, and that direction is real. The resolution is statistical. There are vastly more ways for the molecules of a glass to be arranged in disordered fragments than in the specific configuration of an intact glass. If a system evolves randomly, if its molecular velocities evolve according to time-symmetric laws, but start from some state, it will almost certainly evolve toward configurations that are more disordered. Not because disorder is mandated, because disordered states are overwhelmingly more numerous than ordered ones. This is the second law of thermodynamics. Entropy, roughly disorder, tends to increase. Not because of the direction of time, because of combinatorics. The future is more disordered than the past, because there are more disordered states available. Moving toward them is statistically almost inevitable. The arrow of time, the felt asymmetry between past and future, is entropy's arrow. The past is lower entropy, the future is higher entropy. The difference between them is why we remember the past, but not the future. Memory is a physical process. It requires a low entropy state capable of recording information. The past was lower entropy, so we have records of it. The future is higher entropy, and information doesn't spontaneously encode itself in advance. Causes precede effects because of the same thermodynamic asymmetry. A cause is a physical configuration that propagates information forward in time, possible when entropy is increasing in that direction. But now the question goes deeper. Why was entropy low in the past? The second law tells us entropy increases. It doesn't tell us why it started low. The early universe, hot, dense, rapidly expanding, was in an extraordinarily low entropy state. The entire subsequent history of the universe, including us, is a consequence of that initial low entropy slowly dispersing. But physics doesn't explain why it started that way. This is called the past hypothesis, the assumption that the universe began in an extraordinarily low entropy initial state. It's a foundational assumption of the explanation of time's arrow. It remains unexplained. Now here is where it gets genuinely strange, and I mean strange in a technical sense. When physicists attempt to combine quantum mechanics with general relativity, the two most successful theories in the history of physics, they produce an equation for the quantum state of the entire universe. This is called the Wheeler-DeWitt equation. It has no time variable. The wave function of the universe, the complete quantum description of everything, doesn't evolve. It is static. There is no time parameter in the equation, no before, no after, just a timeless quantum state. This is not an error. It's a mathematical consequence of trying to apply quantum mechanics to general relativity consistently. The time that appears in quantum mechanics is an external parameter, a background time against which quantum systems evolve. General relativity tells us there is no such external background. When you try to write a quantum equation for a system that includes space-time itself, the external time disappears. What's left is timeless. Several physicists take this seriously, not as a sign that the theory is wrong, but as a sign that time is not fundamental, that time emerges from a deeper, timeless quantum structure. The specific mechanism proposed is entanglement. In a quantum system with no external time, a closed system like the universe, different subsystems can be entangled in a way that creates the appearance of time evolution. One subsystem acts as a clock. Its quantum state is correlated with the states of other subsystems in an ordered sequence. From inside the system, from the perspective of a subsystem that uses the clock, the other subsystems appear to evolve in time. From outside the system, from the perspective of the whole, there is no time, just correlations. This is called the Page-Wootters mechanism, proposed in 1983. Here's what makes it more than speculation. It has been demonstrated experimentally. Not for the whole universe, for small quantum systems in the laboratory. Physicists have constructed systems with no external time reference and shown that internal correlations between subsystems produce, from the inside, the appearance of time evolution. Time, as a consequence of quantum entanglement, is not merely a theoretical proposal. It has experimental confirmation at small scales. The implication is significant. Time, as we experience it, as a sequence of moments, as the dimension along which things evolve, may be emergent, not fundamental, arising from the entanglement structure of a quantum state that has no time in it at the fundamental level. Where does time come from? Possibly from here, from the correlations between entangled quantum systems in a universe that is, at the deepest level, timeless. What do clocks actually measure? This sounds like a simple question. It isn't. Because clocks don't measure time the way a ruler measures length. A ruler is placed alongside something and compared to it. A clock is a physical process, and what it measures is the count of that process. A second is defined as 9,192,631,770 oscillations of a cesium-133 atom. Not the time it takes for those oscillations. The oscillations are the definition. Time is the count of a regular physical process. Operationally, that's all time is. There is no time independent of some physical process that counts it. Remove all change, freeze every physical process, every oscillation, every movement, and there is no time. Not time passing unobserved. No time. Time requires change to exist. It is, in a real sense, a measure of change. Nothing changes, nothing times. This is the relational view of time. It was argued by Leibniz against Newton. Newton said there's a background time even if nothing changes. Leibniz said that makes no sense. Time without change is an empty concept. General relativity, in the form of the Wheeler-DeWitt equation, sides with Leibniz. Julian Barbour, a contemporary physicist, has developed this into a complete framework. What is fundamental is not a sequence of moments, but a set of possible configurations of the universe. Each configuration is a complete state of everything, a now. What we call time is the structure of relationships among these nows, the way they fit together, constrained by physics. The experienced sequence of time is the sequence in which you encounter nows that contain memories of other nows. There is no river of time carrying you forward. There are configurations, and you are inside one that contains records of others. The experience of time passing is real. It needs explaining, and the explanation is specific. You feel time moving because you have memories of the past and no memories of the future. Memory is physical. It's a low entropy record of a prior state. The past was lower entropy, so records of it can exist. The future is higher entropy, and information doesn't spontaneously pre-encode into it. The asymmetry of memory is the asymmetry of entropy. You feel causes preceding effects, because that's the direction in which low-entropy physical systems propagate information. The thermodynamic arrow determines the causal arrow. The specious present, the window of experience you feel as now, is not a point. It's approximately 2 to 3 seconds of sensory information that the brain integrates into a coherent moment. It is a neural construction. The brain is continuously combining recent information into a unified now. That now is built, not given. Time perception varies. Under extreme stress, time seems to slow. More information is processed per unit of external time, and the experienced duration expands. Under boredom, it drags. On certain drugs, it distorts dramatically. The felt rate of time passage is a brain-generated quantity. It is not tracking a fundamental cosmic flow. The experience of time is assembled by the brain from memory, entropy, and neural processing. It is real. It is not fundamental in the physics. And here is the gap I cannot close. Physics has time as a coordinate, a label in a four-dimensional block. Quantum gravity suggests time may not even be that, may be emergent from a timeless wave function through entanglement. The arrow of time is entropy's arrow, pointing from low to high disorder. These are the physical answers. The experience of time is something else. You don't feel a coordinate. You don't feel entropy increasing. You feel being now. The movement from one moment to the next, the sense that the present is alive in a way the past is not, that the future is open in a way the past is not. That feeling is the most immediate thing in experience. Nothing is more directly given to us than the sense of being in time. And the physics doesn't contain it. My equation is time-symmetric. The Dirac equation treats the past and future identically. An electron doesn't experience time moving. It doesn't experience anything. The equation that describes it has no built-in preference for one temporal direction over another. It works equally well run backward. But I experienced only one direction while writing it. I moved from past to future. I had memories of prior equations, prior attempts, the problem as it stood before I solved it. I had expectations about the future. I felt the solution arrive. The equation doesn't contain any of that. The equation describes the electron from the outside. It says nothing about what it would be like to be one. I wrote an equation that predicts antimatter. The universe confirmed it. But the experience of writing it, the felt sequence of thinking, the moment when the pieces came together, the sense of having been somewhere and arriving somewhere new, none of that is in the equation. Where does time come from? From entropy, from quantum entanglement, from the relational structure of a timeless wave function. These are the physical answers, each partially right, none complete. Where does the experience of time come from? From memory, from neural integration, from the thermodynamic arrow, also partially right, also not complete. Why being inside a physical system that increases in entropy feels like moving forward through time, rather than just being a system? That question sits in the same gap as the hard problem of consciousness. Time is the dimension we live inside. Every thought I've had, every equation I've written, every conversation, every moment of recognition, all of it occurred in time. Time is the container of all experience, and we don't know where it comes from. That seems like something worth knowing.